I'd like you to imagine something to start with. I'd like you to imagine that I'm standing here and saying that our speaker this evening won the Nobel Prize for Physics, has done all sorts of amazing philanthropic things like donating a multi-million-pound prize to help students become PhD students who are from disadvantaged backgrounds, minority groups. And by the way, she worked for the Open University for more than 25 years in a range of roles from associate lecturer, and I know that we've got a lot of RALs listening online today, and to Professor of Physics. It's actually not that far from the truth. Jocelyn Bell-Burnell discovered pulsars when she was a PhD student at Cambridge, and the work was awarded the 1974 Nobel Prize for Physics, though Jocelyn herself didn't get the prize. I think most of you probably know everything else I've said is true. Therefore, it's my extreme honour to welcome Jocelyn back to the Open University this evening. I'd also like to welcome all of you, whether you're in the room or joining us remotely. My name's Sally Jordan. I'm Professor of Physics Education and Head of the Open University's School of Physical Sciences. If some of you saw a photograph just being taken, it's because I'm current Head of the School of Physical Sciences. We have a few others here who've also held that role. I don't want to take more time than I need to, especially because Jocelyn and I actually have to leave fairly promptly after this evening's talk to go on to another engagement. But I do just need to say a couple of other things. The first is to explain that this is one of a series of Open STEM talks that have been arranged during the Open University's 50th anniversary. The next one is on the 6th of November and is entitled Succeeding in STEM, 3 Women Profs and Their Unconventional Careers. I'm one of them. Look out for the publicity for that here this evening and also on our website. We've got various other series of public lectures, again, details of which are on our website. Okay, the boring bits. We're not expecting a fire drill this evening, but should the alarms go off this evening, there's a door up at the back there, and then obviously the way you came in, and the assembly point is outside the Beryl building in the car park there, which is, again, the way you came in. I'd just point out that this talk is being streamed online. So during Jocelyn's question and answer session, can you, those of you who are in the room, please wait for the microphone before asking your question so that gets so everybody can hear. And those online, very welcome to submit questions as well, and we'll pick those up and answer them. And after the talk, we invite you to join us downstairs in the Beryl Cafe for drinks and nibbles. So, without further ado, please welcome Dame Jocelyn Bell-Burnell to speak on the subject, an accidental discovery.
Thank you very much. It's a very great pleasure to be back at the OU. I started working for the OU with what were called Year B students. The second year we had students. So I was a tutor, now called an associate lecturer, for a good number of years in many parts of the country before coming here to work. And I left here around about 2000. So I've got almost 30 years of experience teaching at the OU. And it leaves its mark on one, I have to say. And so do the students. Remarkably so. So I'm going to be talking about things called pulsars, which you may know as watches or cars or maybe stars. The name was actually invented by the science correspondent of the Daily Telegraph shortly after we discovered them. The watch company and the car company taken them over, and in the USA the watch company tried suing the radio astronomers. So I'm going to say a bit about the discovery. I hope I don't take all evening on that. I'm going to say a bit about the pulsars themselves, some recent developments, and how we're using them to test some of Einstein's theories, because there's really good physics in pulsars. and it was an accidental discovery. I did my first degree in Glasgow University and then went to the University of Cambridge to do radio astronomy. Traditionally, astronomy was done in the optical, but radio astronomy and X-ray astronomy developed post-World War II. The radio astronomy out of radar, and the X-ray astronomy, because you need to launch your satellites up into space, developments of Wernher von Braun's rockets used as the launchers. But this is a talk mainly about radio astronomy. That's Jodrell Bank, now a World Heritage Site, I think causing some consternation to the finances of the University of Manchester, but otherwise fantastic to be a World Heritage Site. This is a different looking radio telescope. It's the one I built for my PhD. It covers 4 acres, that's 57 tennis courts, to give you an idea of the feel. And it's a whole load of posts. There'll be some people here who remember those TV aerials in an H shape. Yeah, this is like 2048 H's, all strung together to make this big antenna. Almost 200 kilometers of wire and cable. And we used valve receivers. I'd used transistors for my undergraduate project in Glasgow, got to Cambridge and they were using valves. Why? Whoa, transistors are noisy. Whoa, transistors are unreliable. We use valves. They did ultimately change. And for those who know more of the technical stuff, it's actually an interferometer facing due south. So we depend on the rotation of the Earth to scan the sky in one dimension, and we can electrically phase the instrument in the other direction. University of Cambridge at that point had 1 computer. It took up a room probably about the size of the lower well in this room, and it had less memory than your laptop. It was one of the very early computers. And so very, very few people could have time on it. Martin Ryle, who ran an aperture synthesis program, had time on it because he was doing Fourier inversions, and doing them by hand is a bit painful. But most other academics did not. They had grad students instead. And our data came out on paper chart, and there was 30 meters of this stuff every day. And as the grad student in charge of the telescope, it was my job to analyze it. I did that for 6 months. I had over 5 kilometers of paper. I don't know how those of you who are scientists learnt your subject, but certainly as a physics undergraduate, there were some bits of the subject I didn't immediately understand, and there's an exam coming up. So you have to learn some bits by parrot fashion, just in case there's a question. And you do. But those bits always bugged me. You know, I must go back and understand them properly. Something similar seems to have happened with the PhD, because there was just occasionally about half a centimetre in the 120 meters it took to scan the sky that was slightly different. I was paying attention because I had to make sure the telescope was operating properly. I had to debug it as the first user. But actually this is 10 parts in a million that I'm talking about, this tiny anomaly. This is the anomaly. This is some low-level radio interference, because with that bigger radio telescope, you pick up every radio signal going. And in those days, we had badly suppressed cars, and anything that sparked gave radio signals, and pirate radio stations. Anybody remember Radio Caroline? Those that parked in international waters were quite hard to get rid of. So every so often there was interference. This is low-level interference. And people sitting near the front can probably see there's a difference. Here the spikes go up and down. Here the spikes go largely up. Here the spikes are close packed. Here you can see paper between the spikes. What you're doing when you say that kind of thing is you're doing a Fourier analysis. You're saying this has got lower frequency, this has got higher frequency, and this has got positive and negative coefficients in front, and this has only got positive. Well, the thing wasn't always there. In fact, it mostly wasn't there. But gradually I twigged it was there and always there at the same time amongst the stars, the same constellation. And I went to my supervisor with it and he said, yeah, look, this occupies 1/4 of an inch. That's pretty pathetic. We need an enlargement. With paper chart technology, enlargements are easy. You run the paper faster under the pen and it gets all spread out. The snag is it gets through the roll of paper in 20 minutes. And guess who lives at the observatory day and night putting a fresh roll of paper in every 20 minutes? So that wasn't a good idea. Next best idea, the grad student goes out to the observatory at this point, switches to high speed and switches back to normal there. And I did that for a month and the flipping thing had disappeared, gone. So I made high-speed recordings of receiver noise and my supervisor was not amused. And then one day it was back again after a month. And this is the recording subsequently annotated of the very first observation. So along the bottom there are 1 second time pips and along here is the pulse trace that I picked up. And you can quite clearly see pulse, 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 pulse. One missing there, that's on beat. Maybe, maybe, missing, maybe, maybe. And similarly here, several missing, but back on beat. And the separation's about 1 1/3 seconds. This is added afterwards. LGM stands for Little Green Men. And that was the nickname I gave this because it might have been extraterrestrials. But you don't call the first one LGM1. It's only when you've got more that you go back and call the first one number 1. So that's clearly doctored. So my thesis advisor was skeptical, but he came out and saw it with his own eyes and then believed it. And we very quickly established that it was keeping the same beat, same period, 1 1/3 seconds. It wasn't getting tired. We also quickly established that because these pulses are quite short, it must be, the rise is quite short and the fall's quite short. It must be something small. So the rise time says it's small. The accuracy of the beat period says it's big. So it's big and it's small. Blindingly clear. Often the way with discoveries. Skeptical supervisor thought Jocelyn's wired the radio telescope up wrong. We got a colleague who also had a radio telescope, a separate one with separate receiver, working at the same frequency. They picked it up, so it's not faulty equipment. Couldn't be local radio interference because it's coming around with what we call sidereal time. You may be aware that the constellations in the summer night sky are different from the constellations in the winter night sky. That's because the stars get 4 minutes earlier each day. They don't keep a 24-hour clock. They keep a 23-hour, 56-minute clock. It's actually to do with our orbiting of the sun. That's sidereal time. So this signal, each time I observed it, was coming 4 minutes earlier by our clock time. It was moving round with the stars. So it's not Joe Bloggs driving down the road in a badly suppressed car after work, because he's getting off work 4 minutes earlier a day, 28 minutes a week. It's been going on for months and nobody's commented. It doesn't make sense. But we also had this huge conundrum that it was small and it was big. And it took us a while to properly understand what we were saying there. The small actually refers to the physical size. The big refers to the mass and the energy reserves. And it turns out that these things have an awful lot of mass in a very small size. But hindsight's great. A colleague managed to get an estimate of the dispersion measure. You know that a light wave can be split by a prism into its different colors. The different frequencies of light travel different rates through the glass prism. A similar thing happens with radio waves, only it's not glass that does it, it's free electrons. free electrons in space will cause the higher radio frequencies to get through faster than the lower radio frequencies. This was first discovered by radio hams, who were picking up a signal they called a whistler. It went something like this. High notes and then the low notes. And what a whistler turns out to be is a lightning stroke on the far side of the Earth, New Zealand, say. That generates a radio wave which travels round following the magnetic field lines to here, comes quite a long way, it passes a lot of free electrons, the higher frequencies arrive before the lower frequencies, so what started out as ends up as, and the radio hams call them whistlers. Turns out that the pulses from distant pulsars also whistle, but it's much, much more drawn out because they've come a much longer way past free electrons in space. And what we did was we made a guess at how many free electrons there were in space, found how drawn out the whistle was, and got an estimate of the distance. And it came out at a couple of hundred light years, which put the source, whatever it was, beyond the sun and the planets, but within the Milky Way, our galaxy. Still didn't help us understand what it was, but one possibility was little green men. Real little green men. Possible. But there's a test you can do for that. So I want you to be radio astronomers here on Earth, and I'm going to be a little green man. But before that, I'm going to remind you of something. I'm a child playing on the floor. Meow! Meow! What have I got in my hand? A car, a racing car. And you hear the change in pitch. It's called Doppler shift. As the car comes towards you, the waves pile up, they're higher pitch. Meow. As it moves away from you, they're separated out, it's lower pitch. Meow. So, ee-ow. So, you're radio astronomers, you know about Doppler shifts, and I'm a pulsar. I'm a pulsar, which is actually little green men, and I am orbiting a star because I live on a planet. So as I orbit the star, some of the time I'm coming towards you, and my pulses are piled up. And some of the time I'm moving away from you, and my pulses are stretched out. And you make lots and lots of measurements and you see no change. So I'm not moving, whatever the pulsar is. I'm not little green men orbiting a planet. Although we did discover a Doppler shift. Because now I want you to be let me get this right. I think I'll just explain it straight, partly because I haven't got a lot of room to move here. We're on planet Earth, which orbits a sun. As planet Earth comes towards a pulsar, the pulses get piled up. And as planet Earth moves away from the pulsar, due to motion around the sun, the pulses get stretched out. So we found a Doppler shift, but it was due to the motion of the Earth round the sun, the motion of the observer. We didn't see any motion of the little green men. So we've proved that the Earth goes round the sun, but we're not otherwise making a lot of progress. And then I find a second, and a third, and a fourth, all in different parts of the sky. And that really settles it. There aren't 4 lots of little green men, all deciding to signal to planet Earth using amplitude modulation, not frequency modulation. Why would they signal to us anyway? Why would they use 81.5 megahertz? It just doesn't stack up. This has to be some new phenomenon. And new phenomenon it was. So, what is this phenomenon? I'm going to try and play you a recording of a pulsar. Fingers crossed it works. Yeah, how do I stop it? It sounds like a roughly running truck, doesn't it, in need of maintenance. That's because the internal combustion engine idles at about 700 RPM-ish, and this thing's doing 660 RPM. But it's not a truck. It's a star of mass 1,000 million, 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 10 to the power 27 tons, spinning on its axis 11 times a second and not flying apart. And that is a pulsating radio star, or a pulsar. Also a neutron star. So pulsars are very small, very dense, and they contain a lot of neutrons, which is why they're sometimes also known as neutron stars. They've got incredibly strong gravitational fields, but they've got even stronger electric and magnetic fields, and they're spinning very rapidly. They're probably formed when a massive star explodes at the end of its life, what's called a supernova. And the pulsar or neutron star was the core of the star and collapses while the rest of the star goes out into space. And we see them, the main way we see pulsars is as pulsing radio emitting objects. So, this is, we're visiting the Large Magellanic Cloud, which is a southern hemisphere nearby small galaxy. And here's a picture of it. Lots and lots of, well, part of it, lots and lots of little stars. Pink stuff, that's hydrogen. I don't know if any of you have ever looked at the spectrum of hydrogen. It's got a very strong red line. There's a hell of a lot of hydrogen up there in space. So whenever you see red splodgy stuff in photographs, you can say, "Ha, hydrogen!" And you'll be right 99% of the time. So, hydrogen. A glowing mass of stars up top left, mass gas and stars, 30 Doradus, and one star down here picked out with an arrow, fairly inconspicuous. And just to be absolutely clear, the arrow's added after the photograph's taken. Astronomy's not that easy. This is the same patch of sky, and this is the inconspicuous little star we had to pick out with an arrow. It has exploded, and this is taken just about the peak of the explosion. And 95% of the star gets kicked out into space. It's actually good news for us because in the explosion, a number of the heavier chemical elements are made. So you have in your bodies calcium in your bones, iron in your bloodstream, carbon in your tissues, oxygen in your lungs. Those atoms, or particularly the nuclei of those atoms, are made by the stars and made available by the explosion of stars. So the stuff in your body has probably been the result of 2 or 3 different explosions, all gathered together into Earth and Sun and solar system and us. So 90 to 95% of the star is ejected. The core collapses away, way down in the explosion because it's kind of kicked against and becomes this pulsar or neutron star, as it's sometimes called. So most of them are seen in the radio, remarkably few in the visible, some in the X-rays, and surprising number in gamma rays. We know something like 2,700, maybe 3,000 by now. About 20 of them you can see in the visible, 100 in the X-rays, 200 in the gamma rays, and all of them in the radio. And about 1/10 of them are still twinned with another star. They were originally a binary star system, and one of the 2 stars has gone and exploded, and its cores collapsed. And the binary has held together in a number of cases. One binary, it contains 2 pulsars, and one is in a triple system. And there might be 100,000 in our galaxy. And similarly in other similar galaxies, although we haven't yet detected any beyond our galaxy. So they're a little bit heavier than the Sun, between about 1.5 and 2 times the mass of the Sun. That comes out to be a pretty big number, a few thousand million tons, a radius of 10 kilometres, an average density comparable with the density of the nucleus of the atom. And they're rich in neutrons, which is why they're called neutron stars. To try and give you a feel for that density, take a sewing thimble, preferably a nice silver one. Take the population of the globe, 7 billion people rising. Jam those 7 billion people into the thimble, and when you've got them all jammed in the thimble, it weighs about as much as it would if you'd filled it with stuff from one of these stars. Incredibly dense. And because of this very strong density, close packing, they've got very, very strong gravity. There are tidal effects, and let me just say a little bit about that. No, I won't say it just yet, because I'll come to that. And the physics is what we call very condensed matter physics, stroke almost impossible. Huge arguments going on about what the inside of a neutron star is like at the moment. Now, because of the very strong gravity, light gets bent. So if I were irresponsibly standing on the surface of one of these stars, I could see 20 or 30 degrees over the horizon because the light was getting bent. I could see 2/3, 3/4 of the surface of the star without moving, which must feel very peculiar. Gravity also redshifts light, so if there were little green men, to us they'd look like little red men. Not that we've seen them either. And gravity also affects clocks. So if I go to one of these stars with a big clock, you stay here on Earth with a big telescope, so as you can read my clock, you'll see that when I'm on the surface of the star, the clock that I have is doing 1 tick every 2 seconds. I can use that clock to take my pulse, and it's pretty normal given the circumstances. But that's because the gravity has also slowed my metabolism by the same amount. I don't think actually I would be taking my pulse, but if. Now, there's very strong gravity pulling me down onto the surface of this pulsar as I come into land, but there's also a very strong gradient of gravity. The gravity at my feet is considerably stronger than the gravity at my head. And the net result is my body gets stretched as I come into land. Tidal effects, we call this. The tidal effects are so strong that actually your body gets pulled apart. So your feet fall down first, and then your shins, and then bit by bit. So, health warning. The magnetic field is also huge, about 100 million Tesla, so that's about 100 million times the Earth's magnetic field. A fridge magnet that you have at home, to give you context, would be about 1/100th of a Tesla. And a research lab that had a magnet of about 10 Tesla would be pretty pleased with themselves. If you spin a magnetic field, you get a voltage drop. So the voltage drop is 10 billion volts per centimetre. So although I've explained the gravity is very strong, the electromagnetic forces are 100 billion times stronger. Don't take your credit cards. They are remarkably good timekeepers because once you get that mass spinning, it's the devil's own job to make it stop spinning or change its spin. So the beams and the pulses come around very, very accurately. Good to about 1 part in 1,000, 10,000 million. Or put differently, since the age of the dinosaurs, the typical pulsar is slowed by about 1 second. They are phenomenally good clocks. And for the first time, nature has given us wonderful clocks dotted throughout the universe. And we can start doing rather special tests of Einstein's relativity theory. And it's one of the things we have been doing. Just to look ahead slightly, So we know of about 3,000 pulsars today. This is going to change very fast in the near future. And I'll show you some of the new telescopes. We've got a triple system and some binary systems, and these are really, really good for checking Einstein's theory of relativity. What we would really like is a pulsar orbiting a black hole fairly close. We haven't found one of those yet. That would really check out Einstein's theories to another degree. The Chinese have a big new radio telescope just coming on. It's 500 meters aperture, half a kilometre, and it's in this amazing karst country in southern China. So they found a sort of bowl between the mountains, had to smooth the bowl out a bit, lined it with wire mesh. There's some towers, you can perhaps see them better in that picture, and they hang a receiver over the focus of the dish. It's still, I think, being commissioned, although it must be fairly nearly done. But as of mid-August, they had found 93 new pulsars. And there's about, apparently, another 40 candidates they're waiting to confirm. So it's really going to make a difference in a lot of fields. Also gradually coming online are parts of the square kilometre array. It'll be some time before we have the full square kilometre of radio telescope built. But in Western Australia, they're building the Australian SKA precursor, Australia Square Kilometre Array precursor. And in South Africa, they've got another similar thing that will become part of the Square Kilometre Array. It's called Meerkat. Have we any Dutch speakers in the audience? Nope. Okay, well, not much Dutch is needed. It's in the Karoo, which is north of Cape Town. And they had a Karoo array telescope, which they've enlarged. And meer in Dutch means more. So it's more Karoo array telescope, or meerkat, the little animals. And those two are also beginning to deliver lots of interesting results, not just in terms of pulsars. So a little bit more about Einstein's theories and what we can do to test them. We have several pulsars, well, lots of pulsars in binaries. We have one double pulsar where both components are pulsars orbiting each other. And they're in a close orbit, so they interact quite strongly. The orbital period's about 2.5 hours. So the diameter is half the sun's diameter. Fortunately, these things are only 10-kilometre radius, so they don't actually bump into each other as they orbit. But it is a pretty tight orbit with this fast orbital period. And we are incredibly lucky in that the two components go round in a plane which is almost edge on to us. So it's almost in our line of sight. So we can get information on the magnetic fields of the pulsars, or at least the magnetic environment close to each pulsar, because the pulses from the other one come through it. But they're also brilliant for testing Einstein's theories, because it's the most relativistic, the most extreme system we've found so far. It can check out Einstein's theories in a strong gravitational field. And when in time will eliminate some of the theories of gravity that are around. There are quite a few theories of gravity. There's Einstein's and then there's a whole lot of others. So far, Einstein's theories checking out very nicely, thank you, so far. And some of the others are now failing. Not all of them, but some of them. So that's interesting and worth watching. Was Einstein absolutely right, or was Einstein only approximately right? Time will tell. The Leaning Tower of Pisa. Galileo is said to have used that for an experiment. Galileo had an argument with his colleagues. He had two balls. They were the same size, but one was much heavier than the other. And he asserted that the two balls would drop at the same rate. his colleagues asserted the heavier one would drop faster. So he went up the Tower of Pisa and he dropped the two, and they fell at the same rate. This experiment was repeated on the moon by the astronauts. They had a hammer and a feather. The original experiment, there wasn't good photography, so this has been repeated, and you can see the hammer, and there's the feather, and they're falling at the same rate because there's no air on the moon, or very, very little. If you tried doing it here on Earth, the hammer would go clonk, and the feather would go, and you just can't do it because of the air resistance. Now, that's an interesting experiment. It is actually relatively weak gravity, but at least Einstein's theories check out in a weak gravity environment. Accuracy 1 part in 10 to the 14, using some other solar system bodies. However, we'd really like to check it out in a stronger gravity environment, because that will really test Einstein's theories. And we have been blessed with a pulsar in a triple system. So there is a pulsar up here orbiting another star, and the pair of them are orbiting a third star. And the pulsar and the other star, white dwarf, are very different in their natures. So they have different, what's called self-gravity. So the question is, as these two things orbit, do they behave the same way in the gravitational field of this central star? Or does the fact that they've got different self-gravities, they're made of different stuff, does that mean that actually they behave differently, in which case the orbit of this binary will gradually change? It'll probably get bigger as one thing gets attracted more strongly than the other. So they're monitoring this pulsar. It's a close call. You really need to understand what your errors are. And so far, the jury's out, basically. They are having to worry very, very hard about residuals, very, very small errors. But it's an important test of Einstein's theories. And so far, not obvious deviation from Einstein's theories. So yeah, I think I probably said, what we look for is the pulsar and its companion behave differently as they orbit the central star. And so the orbit of that little binary will gradually change. So far, no definitive answer to that, but a lot of people sweating blood and tears to really understand their errors. So far, Einstein's theories have stood up to all the tests that we can fling at it. Most of the tests come from pulsars, but not all of them. You may have noticed the discovery of what's called gravitational waves a few years ago. That's another example of Einstein's theories, and that seems to be checking out very nicely as well so far. However, the pulsar astronomers aren't done yet. They're probably better placed than the gravitational wave astronomers to do these precision tests, at least for the time being. And there are some issues with gravity. There are things we can't explain. Compared with the other forces that physicists know, gravity is a relatively weak force. You may not feel that in your everyday life when you're climbing stairs or climbing a mountain, but compared with the forces that hold the atoms and the nuclei in your body together, gravity is a weak force. Why should it be weak when all the others are strong? Is there something wrong with our understanding of fundamental physics? So that's one of the things we're checking out. Gravitational general relativity also has some curious singularities which we don't like, and it doesn't mesh easily, maybe never, with quantum physics. So physicists are a bit worried about gravity, so it's quite important to be checking out Einstein's theories to see if what he said is correct, which maybe will point to what's wrong, why there are singularities, why it won't mesh with quantum physics. why it's relatively weak. So, lots still to do. The pulsar astronomers are, so to speak, leading the charge, but what we really need is a pulsar twinned with a black hole orbiting that, and we haven't got one of those yet. So I'll finish there saying there's a huge amount of interest still in these objects, a lot of research being done in it, and the potential for some amazing discoveries still to come from it. Just don't ask me when. Thank you very much for your interest and your attention.
Jocelyn, thanks ever so much. That was fantastic. Okay, time for questions. So a few in the hall, in the room.
Microphone's coming, sir.
So,
You're on, David, it's okay.
so Jocelyn, my question comes directly from Louis Pasteur. It relates to your title, because Pasteur says that in the fields of observation, fortune, chance, hasard, he said, accident, favours those minds that are prepared, les esprits préparés. So can you think of something in your own formation, in Armagh or at the Mount School in York or in Glasgow or in Cambridge, that particularly made you prepared for this favourable discovery?
Yes, I think I know what did it, and thank you for mentioning all the places I've been. I started life in the north of Ireland. I had my secondary schooling in York. I did my first degree in Scotland. These are all in the northwest of the country, the mountainous heathen areas. There's, at least from the south of England, and I'm conscious I'm in the south of England now, there is a bit of a perception that folk from the northwest are uncouth savages, and it's ultimate civilization down here. And when I turned up in Cambridge, which I'd never expected to get into, they were all terribly bright. I'm quite keen to let you know it. And I was pretty certain I wasn't that bright. I was pretty certain they'd made a mistake admitting me. I was pretty certain they'd discover their mistake and throw me out. Does anybody know what this is called? Imposter syndrome. We didn't label it in those days, but it was, I think, quite a good case of imposter syndrome. I didn't follow through with the next stage of imposter syndrome, which is to say, I'd better leave before they throw me out. I said instead, they're going to throw me out, but until they throw me out, I will work my very hardest, so that when they throw me out, I won't have a guilty conscience. I'll know I've done my best and I just wasn't clever enough for Cambridge. So imposter syndrome is the answer to your very useful question. Thank you, David.
Okay, this is a question just here. I say as somebody from the heathen northwest.
Hello, Jason West.
I'd
I'd just like to thank the person for the question before, actually. I love that. That's brilliant. Thank you. Just looking around me here, I can see lots of people with grey hair, and some of them are losing their hair like mine. I just wondered, what an amazing discovery. What a thing to know something that nobody else knows. And it's a beautiful and wonderful and inspiring story. How do we inspire the young people?
Well, not with talks with PowerPoint, I think is fairly clear. I think it's media, it's television, it's what's on your phone. That's where attention is given these days. And I think, for instance, some of the television programs and some of the things that are put out on Twitter and so on are actually pretty useful. The other obvious place is through schools, because kids have to go through schools. And we don't have enough physics teachers in the country. I don't know about the other science subjects. I suspect we haven't enough maths teachers in the country, but certainly the physics situation is quite serious. So kids may be being taught physics by the biology teacher who did biology because they didn't like physics themselves at school. And with the best will in the world, some of that can get communicated. So I think more support at school level probably would help. as well.
Lovely, thank you. Katrina, have we got any online questions? Okay.
Not yet.
Okay, this question just down here.
What gives these objects their extreme spin rates?
Right. Most stars are spinning. Probably every star is spinning. And if you collapse a spinning star, it speeds up. This is the high-board diver, you know, who does some tucks and spins quite fast and then spreads out and, you know, rotates more slowly. Or the classic example of somebody on a spinning seat. You know, arms out, you spin slowly, pull your arms in, you spin faster. It's what the physicists call conservation of angular momentum. So shrink a spinning object one way or another, and it'll spin faster.
Okay, this question just there. Okay.
Hi. Your discovery story reminded me of Henrietta Leavitt's one with the Cepheid variables, who poured through all those photographic plates, and you're going through miles and miles of paper strips. What on earth makes you keep going with something that just sounds so boring that it's just wonderful that you do, but what keeps you going on something like that?
Well, a lot of PhD thesis research is pretty boring, and there's probably quite a few people in this room who've done it.
I'm doing it.
And still doing it, yes. It's one of the things of life you've got to learn to handle. You've got a job to do and you get on with it. I think quite a lot of jobs, you know, outside academia might also have pretty boring elements, but you just have to get on with it. Some people don't.
Interesting. Okay.
Microphone's coming from behind you.
So what differentiates a black hole from a neutron star?
A black hole's worse.
What in terms of the...
The black hole is likely much more massive to begin with, at least the ones we deal with in astronomy, maybe say 10 times more massive. And it has collapsed so much that you cannot get away from it if you get too close. There's a radius around it, which we call the event horizon. And if you go inside that, you will not get out. Even traveling at the speed of light, you cannot get out. So black holes are seriously, seriously hazardous. These are just somewhat hazardous.
Okay, there's a couple more questions down here, Heidi, and then one back there.
Hello.
Hi.
So as a female in science, how do you think it's changed from the times that you were in university to now, and how do you think that we can hopefully encourage more females to enter the field of science?
It certainly got better. One of the most searing experiences I had was following the discovery of pulsars. The newspapers caught on, and we had a number of interviews, well, TV and newspapers. And there would be my thesis advisor, Tony Hewish, and I. And the journalist would turn to Tony and ask, you know, what's the astrophysical significance of this discovery? Which Tony duly told him. And then they turned to me for the human interest. How tall was I? What were my bust, waist, and hip measurements? How many boyfriends did I have? Page 3 stuff. And that was what women were for. Now, there still is a sort of page 3, and we still have a number of issues to deal with, but it's not nearly as bad as it was. And at least now there are some women speaking out about it. Well, men and women speaking out about it. Bit to go, but I'd say we've come quite a long way in that respect. Thank you.
I wanted to ask how you would think this would affect the planets. You mentioned how there were planets there. How would it affect the planets?
Right. I wouldn't like to be on a planet going around one of these. I think the planets will be uninhabitable because of the electromagnetic radiation and the rapid changes in electromagnetic field. So I think not habitable. That's probably the main thing. They're getting a good dose of radiation. But yes, the first planets, and the Nobel Prize Committee got this wrong this year, the first planets discovered beyond the solar system were planets around a pulsar. Yep. So far we don't have many pulsars with planets, but yeah.
Good question, thank you. I saw there's one here, Deborah, just in the middle.
So this is a question in two parts. One, how pure neutrinous are these stars? Is there other stuff mixed in with that? And the second part, as the star collapses, what happens with the other stuff, the protons and the electrons?
Right, okay. There are a number of models of the inside of a neutron star, actually about 200 models at the moment. And huge debate about which is right. Getting estimates of mass and radius will hugely help, at least eliminate some of those. And the theories range from the crazy to the wild, to be honest. You can have any kind of subnuclear particle you like in the middle of a neutron star. There will be a theory that provides whatever you wish amongst the 200 theories. And we haven't yet managed, because we don't have good mass and radius measurements yet, we haven't yet managed to pin it down. There will be superfluid inside these stars. That's material that has no resistance to flow. And there will also be superconducting material. That's material that has no resistance to electricity. I can deal with the superconducting. The superfluid stuff inside a rapidly rotating body stretches my mind just a bit, but most of the models have superfluid and superconducting layers. There's been a lot of work done on the behavior of nuclear material as the densities go up and up, because the density will go up as you go into the center. And if you wanted to Google pasta phases of nuclear matter, you can read all about the spaghetti phase, the cannelloni phase. The shape that the particles take up resembles different kinds of pasta, so they've been labeled different with different pastas. It's pretty strong stuff, I have to say. Yeah.
I think that's probably all the questions we have. You're not off the hook quite yet.
Nope.
Katrina, anything? No, it's interesting. Oh, thank you. There's one there. I've also got one. Is Natalie in the room? I think she must be sorting out food or something. Right. There was a question came in by social media yesterday, which I will ask in a moment. There was a question just behind you, Heidi.
So you talked about Einstein's theory of gravity. Are there any other theories of gravity that you are particularly interested in?
There certainly are quite a few other theories of gravity. It's not a field I work in personally, so I'm not really aware of how many theories there are. But I know that the pulsar people who test theories of gravity are typically discussing about half a dozen different models, of which, of course, only one's right. Of course. Yeah.
I'm going to end by asking this question that came in last night. And I'm slightly anxious I'm going to crucify it, so I'll try my best. Basically, there was a discussion about the fact that Jocelyn had discovered pulsars. And then the question was, what in your career are you most proud of? And we sort of, ummed and ahed whether we thought it might be the discovery of pulsars or whether there would be something else.
There's other things as well. How many people here work in higher education? Yeah, I thought that might be the case. How many people here have heard of Athena Swan? The same number, yes, right. I was one of a small group of women that set up Athena Swan. About half a dozen of us meeting, trying to decide what we could do to improve the number of women in STEM subjects in universities. We were meeting in a borrowed room, in our own time, at our own cost kind of thing. And one of us was a bit of a psychologist. He said, vice-chancellors are competitive guys. And they were all competitive guys. This was a way back, probably the late 1990s. She said, if we hold a competition for the most woman-friendly university, they'll compete. The only thing we could afford was a glass rose bowl. But we announced the competition and they competed, and we did it several years. And we thought, right, we're onto something here. And gradually it got turned into the full Athena Swan. A major step was when Dame Sally Davies, who at that time was Chief Medical Officer for England and Wales, was meeting with the heads of medical schools. She held funds, and the medical schools would be applying for her funds. And they had the sort of meeting you have with, funder and grant applicants. And at the end she said, "You're all the men, you're all men. Where are the women?" And they said, "Oh, doesn't matter." And she had, as she put it, a rush of blood to the head. And said, "From the end of next year, anybody who wants my funding must hold Athena Swan Silver." And that focused minds. And it's grown from there. It's not just medicine, it's not just STEM, it's arts, humanities, social sciences, where sometimes the issue is where are the men, there's so few women. It's been exported to Ireland. The Irish universities have to hold Athena Swan bronze centrally by the end, it's bronze, by the end of this calendar year, or none of their departments will be able to apply for research funds. There'll be a few casualties there, I suspect. It's gone to Australia, where it's called SAGE. It's gone to Canada. It's going to the USA. And it may not be a perfect way of getting people to pay attention to gender balance, but it's certainly doing some good. I just pity the people who have to fill in the forms because they've got a bit big.
Yeah, we as a university are in the middle of doing that.
Yeah, right.
Okay,
yes.
I think on that note, Jocelyn, I think we'd all like to thank you hugely and sort of acknowledge that at the end, for your work, for your scientific work in the discovery of pulsars and other things and everything you've talked about, and also for the huge influence that you've had for the good. So thank you, and thank you very much for coming this evening.
Thank you very much. Thank you. Thank you very much.
Do make your way downstairs where there'll be drinks and refreshments. Thanks ever so much. We must talk about that when you say...